If x plus 5 equals 8, x has to equal 3. There is exactly one answer. But replace that equal sign with an inequality. X plus 5 is greater than or equal to 8, and the solution expands to include 3 and every number larger. Since it is impossible to manually list every number out to infinity, visual representation becomes a requirement to show the full scope of the answer. A one-dimensional number line works for a single variable, but reality is rarely that simple. When you introduce multiple moving pieces simultaneously, you need a different set of tools. Take an equation like y equals 3x minus 2. This maps out as a continuous line across a two-dimensional grid. Changing that into an inequality, y is greater than or equal to 3x minus 2, shifts the solution to a massive territory filling half the plane. Graphing provides a spatial framework for these solutions, allowing us to organize an infinite expanse of numerical possibilities into a clear geometric region. To map out this 2D space, you start by isolating the variable y. This establishes the boundary line, the border that separates valid answers from incorrect ones. Every inequality requires two decisions. First, you pick the line type. If the symbol includes an or equal to condition, like greater than or equal to, you draw a solid line to show the boundary is included in the solution. If the symbol is strictly greater than or less than, you use a dashed line to indicate the boundary is excluded. Second, you choose the territory. The symbol dictates the direction of the solution. You shade above the boundary line for greater than symbols and below it for less than symbols. These two visual rules translate abstract algebraic conditions into a definitive geometric map. If a boundary line is heavily slanted, it can be difficult to tell which side counts as above or below. In these cases, you can verify the territory algebraically. By plugging a simple coordinate like the origin, 0, 0, into the inequality, you can test if that specific spot is a valid solution. If the math statement holds true, that point is part of the correct territory. Because linear boundaries behave consistently, a single successful test proves that every point within that shaded zone is a valid solution. Real-world scenarios often involve multiple intersecting conditions. To solve them, we use a system of inequalities, graphing multiple constraints on a single plane to see where they agree. This graph displays two different inequalities at once. The first creates the green shaded area, and the second creates the yellow. The final solution is exclusively the overlap region, where the infinite possibilities satisfy both mathematical conditions at the same time. However, there is a common error at the intersection point, labeled here as point D. Because this is where the two lines cross, it is often mistaken for a valid solution. In this system, point D is disqualified. Because it sits on a dashed boundary line, it fails to meet the strict requirement of the second inequality. In a system, a point is only a solution if it satisfies every condition. By overlaying these different constraints, we can filter through infinite numerical data to reveal the precise zone of absolute truth.